And welcome everybody. This is the last day of this long week, and we will not bother you too much today. You started this topic yesterday with a keynote from Peter, and I hope, actually, I know that it was probably a very great keynote, and we have a tight or high goal to match, but we'll try our best. So today I'll open this, let's say, one-day introductory course on URLLC with this overview of standardization and use cases. And then after me, there is Israel with wireless access, very important part of achieving ultra-reliable low latency connectivity. Then it will be Jimmy afterwards with some work that he did and insights he has on multi-connectivity, so multiple interfaces to ensure reliability. And finally, Beatrice with her talk on satellite IoT communications and specifically with the perspective on ultra-reliable and low latency. So we'll start today. I just should apologize in advance. I'm home with my kid, so if there are interruptions, I'm sorry. He's 3 years old, so I cannot really explain him much at this point, but I hope it will not happen. So let's start. Um, we'll start with this picture that I guess all of you have seen numerous times. And this is probably the picture that is explaining the crucial difference of 5G with respect to previous standards of mobile cellular for mobile cellular communications. So 5G is basically driven by standardization for 3 service categories. That's the main novelty. Before 5G, everything was about basically starting from GPRS, everything was about having higher data services, which is embedded in this category, enhanced mobile broadband, or some people call it extreme mobile broadband. But there are these 2 new categories, 2 new cornerstones of enhanced 5G services, which are massive IoT or massive machine type communications, the same thing, and ultra reliable and low latency. We can see this, a bit ugly picture, which I didn't have time to make better, but still it shows some interesting things. So in the, let's say, this central part, we can see IMT advanced. That was, let's say, that was the kind of thing that IMT, International Mobile Telecommunications, which was a document issued by ITU, so International Telecommunications Union. So these are the kind of, let's say, performance requirements that were asked from 4G. And then this big octagon is basically what 5G is about. This is IMT 2020. So we can see how all these performance parameters are kind of stretched for the basically order of magnitude. So 5G has a much bigger task to achieve with respect to 4G. And then we can see, for example, here, where are machine type communications or IoT, massive IoT communications. Then we can see also where ultra reliable low latency communications with respect to performance parameters, and then finally, where is this enhanced mobile broadband. And then for specifically for ultra reliable and low latency mobile communications, we have really short latency budgets, order of millisecond, and also for some, let's say, specific purposes, they also want to achieve a very high mobility support. And we'll see, of course, it's understandable from the name, it's ultra reliable and low latency. So these are the main features of this service category. And I put here some forecasts that are like what the 5G will be about. And maybe the take-home messages here would be that, I mean, 5G is an ongoing thing. I mean, it's by no means finished or used in today's networks. So up to 2025, 40% of the global population will have coverage of 5G. So still, I mean, it's not going to be the main mobile cellular standard used globally. Also, I mean, 1 out of 7 connections will be 5G. So this gives you a bit of, let's say, at least forecast. What is the time scale of 5G? I mean, it doesn't end now. It's actually going to be continued in development and in the deployment in many years to come. I also focus on these two facts here, at least forecast facts. So there are a lot of billions, many more than human populations, so billions of IoT connections, roughly together 25 billion in 2025. So that means that actually we are now really having this, at least in terms of forecast, these IoT service categories and IoT use cases driving a lot of deployments. When I say IoT, I understand under this term both massive IoT and ultra-reliable low latency. So these both combined make this IoT niche. And as I also told just a couple of minutes ago, these massive IoT and ultra-reliable low latency are novel service categories, and they actually pose new and novel challenges. Up to 5G, so concluding with 4G, the primary driver was for the evolution of mobile cell networks were like human-oriented services, higher data rates, and that was the main driver. With IoT, the things change, so now we have to support a lot of devices when it comes to massive IoT, and these in ultra-reliable low latency, these devices need some very stringent reliability and latency requirements. And we'll speak briefly about this soon. Why is this important? It's important because it empowers or enables penetration of mobile cellular standards into the new vertical industries or new verticals. So roughly speaking, media and entertainment was the main driver up to 4G. But now with this massive and reliable low latency connectivity, 5G can support new verticals and maybe make profit and business in these verticals as well. So these are like healthcare, so I don't know, remote surgery or monitoring of patients, energy, so like smart grid monitoring and control, automotive, a kind of a blue ocean thing where like the cars are now being equipped with cellular modems, able to communicate with the network, through the network, and also in the side link mode, in device-device mode with one another. And finally, very important segment or vertical is industrial production. So this is where 5G wants to enter and play a significant role. So when we speak about enablers for these service categories, for enhanced mobile broadband, it's a kind of, let's say, well-established way of doing stuff. So it's about massive MIMO, it's about millimeter wave, heterogeneous networking, a lot of small cells and so on. But in a certain way, we can say that it follows the footsteps of previous generations. So it's not radically new in a certain sense. However, massive IoT and ultra-reliable low latency communications, they require a kind of radical changes. When it comes to massive IoT, in a way, LTM and NB-IoT are like the main enablers for this massive connectivity. They indeed originated in 4G, but are and will be continuously improved through 5G releases. So the story over there is not finished by no means. For ultra-reliable low latency communications, they were like the biggest challenge, and a lot of work has been done in release 15 and release 16, and this will continue in release 17 as well. So it's, as I say, the biggest challenge, but also has the highest potential to transform the vertical industries. So if you have a connectivity that imitates or substitutes wireline communications, then you have a lot of, so you can actually replace the old infrastructure, do stuff much more flexibly, but also you can enable a lot of new things which were not which we were not able to do before. And we'll cover some of those when we cover the use cases in the next slides. So what are these ultra-reliable low latency requirements actually? Probably you've seen these numbers before. So the standardization process started in release 14 already, which is a 4G release. And this famous document, technical report 38.913, established the first requirements with respect to ultra-reliable low latency communications. So first of all, they speak about primarily or exclusively they speak about user plane latency. User plane or data plane, the same thing. So they don't really speak about control plane. So when they speak about plane latency, then they define it as a latency that is measured between the interface of protocols from layer 3 and layer 2 at the transmitting end, and interface between protocol 2 and protocol at layer 2 and layer 3 at the receiving end. So it's a kind of, from the perspective of network to network layer on at the communication ends. So it comprises all the latencies, all the delays that are introduced in layer 2 and layer 1, and of course, including the propagation of the signals. And then the requirement is given for the average latency, which is 0.5 milliseconds in the uplink and 0.5 milliseconds for the downlink. And this requirement does not really have an associated high reliability. So it's just the average value. The next requirement is actually much more. So yeah, so here you can see where this latency is measured. So the next requirement is much more interesting, and maybe the one that you've heard so far a lot of times. So reliability requirement, which actually entails latency inherently in it, is that it has to be 5 nines, so 1 minus 10 to the power 5, minus 5, 5 nines reliability for a single packet transmission of 32 bytes with a latency of 1 millisecond. So this requirement is on a very short packet level. It doesn't really take into account a possible, let's say, application scenario. So why is this data, for what this data is meant to be used? Is it this level of granularity? Is it maybe too strict? It's like a single packet, and it's not about, let's say, average or some kind of probabilistic requirement. It's a deterministic requirement. So a single any transmission has to have this very strict, has to satisfy this very strict requirement. So the probability of successful reception should be 5 nines, under 1 millisecond, with all the delays, with all maybe potential retransmissions, acknowledgements sent from the other side, causing these retransmissions and so on. So if we kind of imagine a reliability latency plane, then this is a single point in this plane which defines a kind of rectangle, and then if you are operating within this rectangle, then everything is fine, and if you're out, then nothing is fine. And that's maybe too narrow-minded. So, and some of the research works actually suggests to kind of do some relaxations. So maybe to have, I don't know, 5 nines for 5 milliseconds, let's say, and then 3 nines for 1 millisecond, and maybe 2 nines for 0.5 milliseconds. So a kind of more, let's say, relaxed and more rich definition of what, so kind of reliability latency curve definition of this requirement. For enhanced vehicle to everything, the things are basically the same, but they give a bit, 3GPP gives a bit more lavish budget, so it's about 3 to 10 milliseconds. And it can be side link or via base station or roadside unit is the same thing. Then there is also this notion of availability, which becomes important actually in release 16. That's where for the first time I saw some use of this requirement. So basically the idea is that the radio access network should operate certain fraction of time supporting the target quality of service. So, for example, 99% of the time we have the latency of, I don't know, 1 millisecond and reliability of, I don't know, 5 nines. So that's what this requirement is about. And actually, we'll see later on that this reliability can go well above 5 nines and so on. So basically, almost all the time, the network should provide required quality of service. And that also puts a question like, how can you really measure something like that? I mean, it's if you're talking about 9 nines, I mean, then what is the fraction of time that this network is actually unavailable? How can we certify that? And there are two other important requirements which are valid for all service categories, and they are about control plane. Basically, the first one is mobility interruption time. So the control plane signaling and let's say call management should be such that the terminal does not get disconnected. The user plane cannot reach any base station for a given up to a given time interval. And actually, this target for 5G is 0 seconds, milliseconds, whatever. So it's like 0. So I mean, the terminal should be connected to the network all the time, able to receive and able to exchange data. And then also the latency of the control plane. So basically, the device being in an idle state to being able to start exchanging data. So transiting from the idle to the active state should be up to 10 milliseconds. So this is a kind of, let's say, this is a higher budget in terms of latency. And we'll see later on that we have this frame structure when it comes to resource organization in 5G. And then the frame is a duration of 10 milliseconds. So basically, you should be able to establish the connection in a span of a single frame. And then I'll wrap up with just a short comment that basically 5G for the first time introduced these requirements. So in 4G, I mean, reliability was not really existing as a requirement. And then there was some kind of latency, suggested latency measures. But I mean, 5G defined these as well. And we should also say that when it comes to these other service categories like enhanced mobile broadband or MIoT, I mean, they also feature requirements that were not really able, that 4G is not really able to fulfill. For example, 4 milliseconds, that's what EMBB wants. And that's, again, something that is not feasible by in 4G. User plane availability of massive IoT use cases is kind of required to be 95%, and that doesn't seem as much, but we should say that, for example, in 4G, the user plane typically gets around 1.9, so 90%, and control plane about 99. So this is again more strict than 4G can achieve. Okay, so we'll briefly cover now use cases. And if you have any questions, just please interrupt me or ask them on the fly so we can discuss them. I'll start with an overview of the, let's say, most important categories and just focus on them. The first is automotive, URLLC or URLLC for intelligent transportation systems. And as I said, this is a kind of a blue ocean scenario because, I mean, up to this point, the cars were not really equipped with communication equipment that could enable them to communicate with each other. So we can see some forecasts that like 90% of new cars will have modems, not necessarily 5G. You can also have 4G. I mean, today we are seeing release 14 devices being made, I feel like fresh, new, not available so far, that can support side link and regular operation that are being put in cars. And some manufacturers are already putting cellular modems in all their vehicles. So in this document that I mentioned, it's stated that new radio, so 5G, shall complement LTE for advanced automotive services and support interworking with LTE. So the message here is that this is not a new thing. I mean, it started with 4G, and then 5G is just enhancing it and complementing it. There is a very rich document mentioned here. So this technical report 22/886, which gives a really detailed overview of many use cases and specifying them very precisely. And of course, I mean, we don't have time to go through this, and it will require probably a whole week. The main things that can be gathered from this document is that there are non-safety or comfort services and then safety-related services. And when we speak about ultra-reliable low-latency communications, safety-related services are basically where such connectivity is required. And there are not that many. So I mentioned here the ones that I found in the document and that are, let's say, really fulfilling this criteria to be categorized as ultra-reliable low latency. So very low latency and very high reliability. And these are remote driving, collective perception of environment, and teleoperated support. And we'll mention briefly just two of them soon. Before proceeding, I just should tell you that this is, I mean, all these services, they feature similar or very common characteristics. So the connectivity should be in a spectrum below 6 gigahertz. Actually, I mean, a lot of bands, a lot of countries are standardizing bands in around 5.9 gigahertz for this vehicle to anything communication. They can feature roadside units, but can also, some of them don't feature them. So it's like side link communications. And of course, we should observe integrity, authentication, and confidentiality of the communication. So remote driving, I guess you have an idea yourself pretty well what this is about. So it's a driver that is actually remotely operating a vehicle, and the connectivity is achieved through the cellular network. And then requirements are like reliability of 5 nines, both in the uplink and in the downlink. And we are talking about very high absolute speeds, so 250 kilometers per hour, maybe too much for today's traffic conditions. End-to-end latency, it's 5 milliseconds, but this is end-to-end. So it's not user plane radio latency that we mentioned a couple of slides ago. And then if you want to estimate how much should be this user plane radio latency, then there is this rule of thumb estimation about, let's say, 10 up to 20%. So we are talking about 0.5 to 1 millisecond. So this is really URLLC scenario. Then in the downlink, we should send some kind of control commands up to 1 megabit per second, probably less in reality. But in the uplink, it's a kind of also has a flavor of this enhanced mobile broadband in a way, because it requires 20 megabits per second. We're talking about sending 2 video streams, so 2 cameras monitoring the conditions on the road and traffic on the vehicle. Another important category is this collective perception of environment, which is basically enabler for a lot of specific use cases. So the cars should be able to exchange information among themselves, maybe through roadside units or directly, and then in this way enable cooperative automated driving, like secure overtaking or lane changing or collision avoidance or emergency trajectory alignment, and so on. So these are just some of the examples of this cooperative automated driving. Here we have an example in which this vehicle C wants to overtake truck B, and then the truck B is signaling to vehicle C that there is actually a vehicle A that vehicle C doesn't see, and which is coming from the opposite direction, and then there is an alarm raised that vehicle C shouldn't actually overtake. So that's one of the scenarios. And this document is actually featuring a lot of such examples given in many details.
Sorry to interrupt you.
Yes.
Just a curiosity, these numbers are taken from the document that you mentioned, right?
Yes, yes.
Oh, okay, thank you.
Yeah. Actually, maybe if we are discussing right now this point, these documents are, of course, as you probably know, they're evolving through releases. So they're becoming richer and richer. So last time when I checked with, which was like 2 years ago, it was not that that much data. So these are, let's say, fresh numbers. And also collective perception of environment didn't really figure out as a kind of collective enabler for many use cases. So I mean, what I'm trying to say is that these things evolve, and then we can expect that maybe next year there will be even more use cases and more numbers. Maybe some of them will get revised. So it's a living thing. Yeah. So what are the requirements? Depending on the context, maybe they can exchange only raw data. There is no time, or there may be pre-processed data. So again, a kind of enhanced mobile broadband. And then the latency and reliability depend on the distance. So if the cars are very close by, we need very high reliability. If they are like a bit further away, then it's less, and so on. So which actually makes sense. And again, this is end-to-end latency. So divide by 10, and then you get the, let's say, radio plane latency, at least the estimate. Another, let's say, very important niche is this cyber physical control applications. Another driver of developments, and there are documents. Actually, this 22104 is pretty fresh. I think it's from the last month, and it gives a lot of details again. I mean, you can, it's really rich and illustrative. And if you want to find, let's say, solid information, I recommend this one. There is also another document, which is a kind of predecessor to this one, to 22261. So in this, I'll quote the numbers for this 22104, which is, let's say, a fresher and a richer version, elaborating these use cases. So we have factories of the future over there. We can also speak about Industry 4.0, more or less the same thing, or smart factories, smart grid control and monitoring, and then connected hospitals. And I'll focus just on 2 use cases from factories of the future, because they give some numbers which illustrate basically a kind of categories that we have within these use cases. There are very nice narratives in the document, but we just don't have time to go through them. So in factories of the future, we have motion control, factory automation, process automation, automated guided vehicles, and so on. And I'll just mention motion control, which is maybe the killer use case in terms of what is expected from the network. So motion control is a closed loop control in which there is a controller, there are actuators, and there are sensors, and of course there is the process that is being under control. And then all the communication is featured in transactions. So sensor sensing the process, giving the data to the motion controller setting action points to actuators, and these actuators act on processes. And then this loop, this transaction happens every 1 to 2 milliseconds. So everything should happen with this kind of periodicity, and that puts a lot of strain on the communication network, because I mean we have basically communication between sensors and motion controller, and then motion controller and actuators, and all this communication and all processing of data should happen within, let's say, 1 or 2 milliseconds. And to make things worse, I mean, setups are such that we actually have a lot of actuators and a lot of sensors, and all the observations have to be isochronous. So they have to share the same clock, because the control crucially depends on them being synchronized. So it's really, and of course in 4G, I mean, when 5G we wanted to do over-the-air synchronization, where we want to avoid cables, so there is no distribution of the clock through some separate other network. And here I put some numbers. They are basically, I mean, it's kind of 3 sub use cases, and what's different among them is that these transfer intervals. So depending on how fast should be the control loop, then we have, let's say, transfer intervals which are like sub millisecond, or let's say of the order of millisecond, or maybe like a couple of milliseconds. But as you can see, here we have this availability requirement. So I mean, very huge numbers. So the network should work almost all the time such that we have end-to-end latency less than transfer interval value, which is like this 500 microseconds, and that we will enable that survival time will not be exceeded. Survival time being how long can the system operate without a new update. And then what are the speeds of the UEs, and how many of them are controlled, and what is the service area. I mean, things are so tight that, I mean, basically the base station and the controller, they will be physically in the same area together with all the actuators and devices. And then you can also see this kind of budget in jitter, so like 500 nanoseconds plus minus. And then for this isochronous operation, we have to achieve like sub microsecond synchronization among all the agents in the network. So it's really let's say highly features a lot of stringent requirements for wireless networking. Process automation, it's a bit more relaxed, let's say. So it's about monitoring processes in which bulk quantities are produced, like chemicals or liquids or gases or whatever. So there are no moving parts over there. So it's less of a risk for, let's say, personnel and so on, and doesn't really have doesn't require that much synchronicity. And then we can see here some typical values for closed loop control, so control of some kind of reactive processes. And then, I mean, here you can, this is maybe the most important point. So transfer interval is 10 milliseconds. So it's like order of magnitude more. So it's much easier to deal with. And then it's just another use case within this process automation is like monitoring. So it's even more relaxed. So now we are not really controlling anything in a closed loop. It's a kind of open loop scenario. And then here we have also the feature that the traffic is predominantly mobile originated. So it's not like it's like reporting when something happens, like the temperature reaches certain value or pressure or something similar. And here we can see that again among these numbers, this is maybe the most important. It's about milliseconds or hundreds of milliseconds to minutes. So now we have a lot of budget for doing nice processing stuff and implementing rich protocols. We can do retransmissions and things like that. In previous use cases, it's not that easy. Okay, and then I proceed with overview of what's being done in order to support these kind of services in 5G releases. So up to date, we are talking about release 15 and release 16, and then the work on release 17 is a kind of ongoing now. Things are a bit shifted with respect to this original timeline. So release 16 was a bit late, 3 months late, and then they're also discussing about delaying release 17. Not much, but still, I think it's about 3 months. And for this release 17, it's the pandemics, because they cannot really work together effectively as before. All these online meetings have their problems, as you know. So what is also important to mention is that we have this new radio started with release 16, but also LTE is evolving continuously through these releases. So LTE is not a finished story. So release 15 was finalized in June 2018, and achieving low latency was a priority because there were some techniques in 4G, like multi-ret, that could foster high reliability, but low latency was the issue. And we'll see what are the techniques to lower the latency. And here is a nice diagram taken from this paper here. You can see it. It's about a downlink, but it's, they have this anatomy of latency components, which is actually, simple, but still very instructive. So we can see what are the kind of times, characteristic times when it comes from transmitting a packet up to like receiving it, and how we can shorten these times in order to make things fulfill the requirements. So there is some kind of signaling. So this is basically about layer 2. So connection request, grant, channel training, feedback, queuing, delay, and so on. Then we have some kind of processing time, encoding and decoding a packet, estimation, extraction of the control information. Then we have actually data transmission time, so TTT. Then we have a kind of propagation time, but propagation time we neglect. We're talking about maybe kilometers, so wireless should be sufficiently fast that we don't really see this delay. And then we have processing at the device, maybe acknowledgements, no acknowledgement sent, non-acknowledgement, and then retransmissions. So all these things have to fit within 1 millisecond and should be actually also very highly reliable. So the main thing now is that wireless frame is 10 millisecond long. So all these, let's say, resources on the wireless channel in 4G and in 5G now, they appear with periodicity of 10 milliseconds. And then these frames have subframes. And then in these frames, we have slots. And then these slots consist of a certain number of symbols. And this is actually what the user gets, what the terminal gets. So the terminal gets a slot. And then this slot is 0.5 milliseconds. And then if you have a latency budget of 1 millisecond, and basically your transmission time is 0.5 milliseconds, that's not good. So they were discussing how to shorten this time to transmit. And then one of the ideas was to actually shorten the symbols. And we can shorten the symbols in time by increasing sub-carrier spacing. So we actually have, let's say, use more frequency, but then we can get shorter time content of the data. And then this is the idea is, as you can see, that these are multiples, these subcarrier spacings. The idea is to make the things backward compatible with 4G, so we can share the same, let's say, physical resources. And that's mentioned here as well. And then basically by increasing subcarrier spacing, we are shortening symbols, and then we are getting less and less time to transmit the symbol. However, this will work for higher frequencies where the delay spread is small, but below 60 gigahertz, this is not a desirable option. So we can see here, for example, that in this outdoor macro coverage, we should use like the ordinary subcarrier spacing. Then in small cells, we can go to bit increased, then indoor wideband, and then finally millimeter wave. But for example, as we mentioned, automotive or maybe this industrial IoT, they will actually use sub 6 gigahertz band. So we cannot really go with this subcarrier, increased subcarrier spacing. So for these scenarios, then they actually propose to use mini slots. So now instead of transmitting all 14 symbols, the terminals can transmit less, like 7, 4, or 2. Some documents say also 3. So the terminal is active just in a part of a slot, and that part is called mini slot. So things are then getting shorter as well. Of course, you can transmit less data, but we are talking about very short packets for such cases, so that's okay. And then, as I said, that the idea is to make things compatible. So these slots, I mean, so you can see here slots. So this is a slot, and this is a slot, and so on. And then we can increase the subcarrier spacing, so we can have a subframe that has different. They call it numerology, but fits nicely because everything is like divisible by 2, and so on. And we can also have mini slots in which we can fit URLLC packets if we are using the same subcarrier spacing. Then the idea was also to reorganize the packet structure to make it pipelined, to allow pipeline processing. So we have resource blocks, and then these resource blocks are, in ordinary case, the things are kind of interspersed, so we can learn. We have pilots, and we can do maybe better channel estimation. But here the idea is that we have pilot and then control region and then the data region successively, so things can get pipelined and processed by pipelined. Then novel coding schemes, I will not go into details, but they have a lower complexity, so again it's a faster thing to do. And then idea was also to reduce the signaling time, so the time to actually put the transmission on the medium. And then for the downlink, it's a kind of easy because we can do this preemptive scheduling. So the ultra-reliable low latency transmission actually preempting, going over the resource blocks that were assigned to, for example, enhanced mobile broadband. So that also creates problems for the EMBB user, but still, I mean, URLLC users, they get priority. For the uplink, things are a bit more difficult to do, but there was this configured grant approach that involves the idea is to give pre-assigned resources in the uplink to users, and they can use them if they experience traffic arrivals. And then because it's not certain if they use them or not, then the idea is to give these resources, to configure these resources in the physical uplink shared channel. So people, I mean, users can get the same or overlapping configured grants. And then like the idea is that we kind of hope that they will not be simultaneously active. But if they are, then the idea is also to allow certain number of repetitions. So each configured grant also involves, let's say, a certain number of repetitions. So the UEs can in that way achieve higher reliability. And then in release 16, the things just get kind of enhanced. So this initial work in release 15 was basically just fine-tuned and improved in release 16. So release 16 was completed this June, and there are not that many nice documents that actually explain all the things that have been done over there. I'll try to just give a brief overview. Also called as 5G Phase 2, and they have a number of novel use cases and advances for different stuff. You can see it here. So for example, there's this 5G LAN type service, which is a novelty, time-sensitive networking to replace Ethernet that is used in industrial setups for this purpose. They also speak about enhanced, ultra-reliable, low latency, satellite access. Beatrice will speak about that, and so on. So this enhanced, ultra-reliable, low latency now, I mean, they even lowered latency, like between 0.5 and 1 millisecond, and they increased the reliability target. What is the actual latency required depends on the use case. But still, we are now seeing that these goals are being even more, let's say, requiring. What are the techniques they use? So if you remember, there was this acknowledgement stuff that I mentioned on some slides ago. So now the problem over there was that the time for feedback and then potential transmission, I mean, the resources occurring for that were not happening with enough granularity so we can achieve actually low latency. There was a problem in scheduling. So they made this uplink control information enhancements, so more opportunities, additional code books to have a lower latency and higher reliability. Then if a device has several, let's say, active connections, then the idea is that to drop the less priority connection. Yeah, I just have to, just a second. Hello? Yes, sorry for that. It was a bit of interrupt. So if there are like URLLC and enhanced modular broadband streams, then URLLC gets priority. Or if there is like acknowledgement, then again URLLC gets priority, and so on and so on. So they have a kind of scheme according to which a terminal should behave if it has different, let's say, control channels or data channels in place. Then there are some enhancements in this physical uplink shared channel for this configured grant, basically. So these mini slots that we mentioned now can occur in the same slot. That is a novelty. In release 15, mini slots cannot happen. Consecutive mini slots cannot happen in the same slot. So there is more time, basically, or let's say more opportunities within less time to repeat your transmissions. Then the next thing is that they also discussed multiplexing in the uplink between different types of services. So if there are some terminals having enhanced mobile broadband and some terminals having ultra-reliable low latency service, then actually they can be scheduled in the same resources. That can be done dynamically. So this UE1 belonging to EMBB got a grant for these resources here. But then this guy, which needs ultra-reliable low latency, appeared, and there is no time to serve this guy. So this guy gets scheduled in a part of the same resources. So it's a kind of preemptive scheduling in the uplink, let's say. And then there is also kind of scheduling in the same resources on purpose. So for example, this guy, URLLC UE2.
Sorry for the interrupt.
Yes.
We can't see your cursor, actually. I don't know.
You cannot see it at all, or you cannot see it now?
No, I think Yeah.
Not at all. Oh yeah. Well, now
there's-
it's a bit too late.
There's a
But
pen symbol on the lower left.
okay.
You have,
Yeah.
try
Sorry,
that
guys.
and see if that.
Yeah. Can you see it now?
Not yet.
Can you see something now?
Oh, okay, yeah.
Sorry. Yeah, exactly. You shouldn't use that one. That may be bad. Are you using PowerPoint or?
It's PowerPoint. It's PowerPoint. No, I'm using the Teams actually. So I don't know.
But
Is this better?
Yeah. Now it's perfect. Yeah.
Cool. Yeah, guys, sorry.
No problem.
Anyway, so this guy got configured grant, but I mean, of course, his activity pattern is not known. So he will potentially use these resources. And then the idea is to schedule UMBB guy, this guy, to schedule in the same resources, hoping that this URLLC guy will not be active. Yeah? And then what to do if there is like a collision? Then one way of dealing that is to send some kind of cancellation indication. So you have to have also improvements in the downlink control channel, asking enhanced mobile broadband guy to stop transmission. Or there is another way, like asking the ultra-reliable low latency guy to increase the power. So he gets actually a chance to capture the resources with respect to the EMBB guy. Okay, and then I've just finished with this slide. When it comes to releases, release 17 is going to continue the work in release 16. Basically, the stuff that I talked so far with new enhancements. Another important thing is this positioning. So very, let's say, for industrial IoT cases, order of, let's say, meter accuracy. Side link for V2X. Then run slicing, so fast access to the cell supporting the intended slice. And then finally, this thing, anything reality. So it's like a composite term for virtual and augmented reality, in which we have a kind of combination of very high data rates and low latency. And that basically sums up the overview of these releases. And I'm just going to wrap up with a very short, let's say, at least personal reflections on machine learning and ultra-reliable low latency communications. But before that, I will actually ask you guys, I mean, do you have any ideas? Where would you like to apply or how to apply machine learning in ultra-reliable low latency communications?
Actually, what came to my mind is with respect to the coding schemes, maybe we can somehow apply machine learning coding schemes to achieve some, efficient codings and all.
Efficient in terms of low complexity.
Yeah.
Yeah.
No, or maybe low latency.
Low latency. Okay, low complexity, low latency.
Yeah.
Okay. Any other ideas?
This is a trick question. This is
it is a trick question.
To listen, if you paid attention to Petar's keynote yesterday.
And actually, I have, for example, in tactile internet scenarios,
yes,
we cannot rely on the communication links feedback. For example, when there is a drop in the communication to the handover and do a proper action. So in those scenarios, we need to somehow predict the blockage in the communication link, right? Okay. So I've seen a lot of papers recently on this, in which they use some machine learning techniques to predict the blockage in the link. For example, in vehicular scenario, they attach a camera, RGB camera to the base station. Yeah,
yes.
That's also feasible, I think.
Yes. Cool. Well, yeah, I mean, this is a good example. The first thing about coding, so there are indeed, let's say, right now, I mean, I could say maybe even a rich literature on machine learning for codings. But the problem over there is that the thing that you mentioned yesterday with Peter, I guess, was, I mean, what is actually the robustness of this approach? So will this work over all SNRs, for example? And then if it will, I mean, can we actually characterize that with this very high reliability? Do we really know? I mean, do we have a guarantee that we can actually achieve this, I don't know, 5 nines deterministically with this approach? And that's actually a huge problem. And then the issue is, yeah, sorry guys, yeah, it's really, I'm really sorry. I just have to, yeah, no kids up. It's my baby son. Yeah. So the thing is that, as I was telling you, we don't really have a nice way so we use machine learning, but we have a model deficiency. And then model deficiency means that we don't know really the process. So that means that, I mean, we cannot really guarantee that we can, what we learn is actually, you know, accurate. So this measure of 5 nines and 1 millisecond with kind of deterministic stuff, it's actually, I would say, in a way, very vague when it comes to has a very vague connection to how we can actually use URLLC over there. And then I investigated a number of papers and preparing for this talk. And I mean, so they may mention ultra-reliable low latency in the title, but then you find out that maybe it's like 2 nines, or maybe it's actually, I don't know, optimizing service coexistence scenarios. So they have, I don't know, better resource use for EMBB and so on. So, I mean, it is a really tricky thing. And if you discuss with Peter this stuff that he was doing with some of our PhD students and postdocs, I mean, it's there is this problem with model and how to actually tame these tails of probability distributions that the models, most of the models cannot cover, because they are actually made for system design for averages. And then, of course, if the model is if the environment or if the system is not stationary, then I mean, how to figure out the new model? So these are open questions. And yeah, Peter probably mentioned this paper of his trying to, let's say, introduce new measures for ultra reliable low latency stuff, this average durability, probably correct reliability. There is also another paper by our former colleague, Ji Hong Park, and he was actually at that time visiting or being postdoc with Mehdi Benis. So in which I also found some, let's say, interesting takes on this problem. So as you mentioned, this predictive ultra-reliable low latency, in which we can use other modalities other than just radio communications. And then what I speak about here about this predictive ultra-reliable low latency is like, can we do what is the required sample complexity of training? So how many actual instances we should use for training to be a kind of, at least probabilistically, can give some kind of probabilistic approach to characterizing the performance. And then, of course, if you need like 5 nines, it's a lot of time. And then they have this idea, multiple agents collaborating in the training phase. For example, federated learning, in which we just exchange some coefficients. But then the issue is over there, of course. I mean, this collaboration, it also takes certain overhead. I mean, exchange of messages and so on. So it's a tricky problem. Another interesting point over there was this perception of error prediction. So I mean, we should actually match let's say, the prediction with the characteristics of the, let's say, entity using this prediction. So if you have a driver, then every couple of seconds is the horizon is okay. But if we have, I don't know, AI driving the car, then maybe we need much less. We have much less time to do that. And this is the final slide, which we mentioned, the concept we already mentioned. It's this multimodal fusion. So cameras to predict some sudden rare events that we cannot really see, let's say, through wireless. And then they speak about, for example, split learning framework in which the neural network can actually can treat different inputs. I don't know, radio, channel observations, and camera feed, and so on. And then with this slide, I finish. I'm a bit over time. Hope it was not too much, too boring, but if there are any questions, please ask.
Sorry, I have a question.
Yes.
With these last two slides, are we implicitly acknowledging that with current state of, let's say, ML approaches, we cannot guarantee, let's say, upper band for, upper limits for latency in ultra reliable communications in wireless?
Well, I would, as I said, I mean, this is my personal opinion. So maybe there are other people have other opinions, but I would say that the challenge is very, very, very tough, and that I don't see at this point, at least, papers suggesting that they can actually do it. And my belief, it's I'm not an expert in machine learning, in designing new algorithms, so I don't know what's going on. But I would say that, I mean, we have to have really high accuracy, and we have to have really, let's say, and we also have to fulfill certain very low latency. So maybe, if, for example, the environment is stationary, and then we can afford, let's say, a very long training phase, knowing that the environment will not change. Then we can use this subsequently. So that in that case, there is, let's say, a hope for the use of machine learning for this in this kind of scenarios. But if you have non-stationary environment, then, I mean, what you learn, if it's not really useful afterwards, then maybe we need to have another, we have to approaches in which we can actually use the old observations, but with certain reliability in themselves. So maybe that's the way to go.
Thank you. Thank you.
Yeah. Okay. If there are no more questions, then
there
I guess
some hands being raised.
Okay, because I cannot see it, and I'm
sorry. This is Stanley.
Yes.
Yes. Thank you for your
okay. Yeah.
presentation. Yeah. And I have a question about the different performance index KPI in the spec.
Okay.
Yeah, since we have different application requirements, so from the application point of view, these index are average or the latency value of it's a kind of general idea. So we don't really know the index, how to measure the index from average or just from a major, maybe a very specific statistic way to calculate the reliability or the latency index. So actually, I'm not asking a question, I would like to discuss about how to what is the correct way to deal with this index. We should treat it as an average way, or we should handle this index from a very specific application-oriented.
Okay. Yes. I think I understood. So I mean, these numbers that I shown, basically, they don't. When they derive, when they want to test the performance, they're using Monte Carlo simulation.
Yes.
That also means that it's a kind of average in a certain sense. But the thing is that, as you see, these numbers are very tough, and they're in a certain sense also a kind of oblivious to the actual application. I mean, they try to have these sub use cases in which they tailor the connectivity to certain, let's say, class. But I would say that they still don't know actually what they need, because it's not really been tested. And especially industrial IoT, when we're now like replacing wires, they don't really know. Maybe they can actually afford to lose some number of packets, or maybe they don't need availability, which is like, I don't know, 9 nines. Maybe the controller is actually able to navigate the process without observations for certain amount of time. But and I would say this is the right venue to go, because eventually you need this data for some kind of application. But then this poses again a problem. I mean, then should we have like a vertical slice for each possible application? So it's a mess when it comes to standardization. But my feeling is that when these things are put in practice, probably a lot of new stuff will be learned in terms of what actually we need, or what actually the use case, the application needs, and then there will be some kind of refinement. And then maybe these meta measures, like we are achieving, I don't know, 5 nines with 6 nines probability, or we are, I don't know, achieving nines with 5 nines and 5 nines with 7 nines, and so on. Maybe this will then be easier to define, and then we can maybe open the way for, let's say, non-deterministic treatment of the problem.
Yes, I think it will be make the measurement more flexible to accommodate these conditions. Yes, and
Yes.
I think one could discuss more offline. And thank you very much.
Thank you. Okay, are there any more hands raised?
No, not what I can see.
Okay, cool. Okay, well, yeah.
Thank you so much.
Thank you for your patience, and thanks for the discussion. And I'm sorry that I was a bit over time.